Hi, in this video, we're going to be looking back at the RTOS in general and some specific aspects of the RTX, okay, to better understand where we are, okay, in the whole RTOS environment. Okay, so we're going to be covering these topics. We're going to look back at why we want the RTOS and what is the motivating factor again, compare it with the super loop approach that we have been using prior to switching over to the OS, and we're going to looking in particular at the RTX and the CMSIS libraries that we have. Now, what exactly is a real-time operating system? Okay, so we have seen this before, but I think it's important for us to get back to understanding the motivation. Okay, so an RTOS is designed to meet very harsh timing constraints. Harsh means critical, important timing constraints. And in essence, when we say real time, it can sort of can be categorized into two separate areas. One we say is hard real time, the other is soft real time. Okay, when we say a particular task is a hard real time, it must be completed on time. Okay, there is no option. Okay, if you do not complete on time, it can lead to total system failure. Whereas a soft real time deadline could mean that even if I have missed the deadline, I can still carry on and I can finish the task, and I do not see any major catastrophic effect, okay, on the overall behavior of the system. Okay, so that is basically the difference between a hard real time and a soft real time. Okay, in terms of industrial applications, RTOS based systems are very widely seen, okay, in robotics, aircraft control, machinery, automotives, and so on. Okay, and the key design requirements, okay, is we are sort of seeing. One thing is predictability and determinism. Okay, so in the few labs that we have already seen with OS, we can predict the behavior very accurately. Okay, and the timing is very deterministic. Okay, we can say very accurately exactly the intervals at which certain events may happen, or when a event may be triggered, and so on. Okay, so that predictability and the speed at which you can respond is very critical. Okay, fail safety are things that we haven't really covered much yet, but yet OS systems have the ability to provide a lot of fail safe options. Okay, and in terms of scheduling and memory allocation, we are using the default scheduling and memory allocation system. Okay, but there are ways in which you can manipulate them. Okay, and that is something that you sort of play around with when you are trying to toggle the OS round robin flag. Okay, and so that is one aspect of it, but there are also other areas that you can manipulate in how the OS actually behaves. Okay, but we're not going to go into all of that. Those are things that you can definitely try on your own. Okay, just to explore how you can actually configure the OS and achieve different type of scheduling behaviors. Okay, so why RTOS and embedded systems is because prior to this, what were we doing? We were having a very huge sequential loop. Okay, and what we had was, for time critical events, we had interrupt service routines. Okay, and of course with that we need to synchronize between the different ISR. Okay, and ISRs are also not so predictable and deterministic, especially once you have nested ISRs. Okay, and we have seen before that when you have multiple nested ISRs, okay, and you have a very uh, adverse effect on the timing delay in the main loop, okay, which is something we do not want. Okay, and the moment I make any change in the ISR or in the main loop, okay, the whole dynamics, the timing dynamics of the system actually changes. Okay, so by switching over to OS, okay, we have a lot of benefits. Okay, as you have seen here. Okay, in terms of the program flow, the multitasking, okay, protecting shared data. Okay, we are also looking at things like communication and transferring information from one task to another task, and so on. And very importantly, you find that it is very easy to develop high level applications, because now you look at everything from a modular perspective. Okay, you look at everything as a task level. Okay, if I want to add some new peripheral block, I create a new task for it, and I see how this task is going to now interact with the rest of the tasks that I have in the system. Okay, so it becomes very easy to scale your system, and that is one of the biggest advantages of going to an OS. Okay, so just to again solidify this point, if I go back to one of the earlier examples, okay, where you have a GPS based system, okay, if you recall in the earlier slides when we were first getting familiarized with the whole software architecture from a single threaded perspective, we had a system where a car can drive around and detect potholes, okay, and update the GPS map and so on. Okay, the same system, okay, but now we just say that instead of detecting potholes, we detect speed cameras. Okay, so as I'm driving around, okay, based on my current GPS location, I can uh, connect to some database and then get this information and sort of warn the driver ahead of time if I'm approaching a speed camera. Okay, so this is the general idea of the whole system, and we saw that we can break it up into a few different tasks, okay, in terms of decoding the GPS, checking the locations, recording my current position, okay, reading my inputs and updating the LCD. Okay, and without the OS, okay, I would have done something like this, a big super loop, okay, where I would have done one task after another task. And the whole challenge comes because uh, you do not know when the GPS device may come, GPS information, okay, and when the GPS position gets updated, what if I just get past, okay, that part of the super loop that is supposed to have used the GPS, okay, then I need to wait for one more cycle. Okay, so it's a lot of unpredictability, okay, in the system in terms of timing response. The real time aspect of a system is lost when I have a super loop. Okay, and as long as any one of these functions change, okay, the whole timing dynamics, okay, the time that I take to complete the super loop will also change. Okay, so it's very easy for the whole dynamics of the system to be affected the moment any one of these tasks has to go through some change, okay, in behavior. So that is the major drawback of this super loop system. Okay, and when we move over to a RTOS, okay, we are free from all this to be able to modularize our objectives into tasks and then focus on developing our tasks to fulfill certain requirements. Okay, so in terms of RTOS, of course, there are different types of RTOS available in the market. Okay, RTX, one of the good things for RTX is it is royalty free and is open source. Okay, of course, it's deterministic because of the real-time capability of it. Now, royalty free and open source are two important aspects. Okay, and why I say that is because if you were to put in some commercial RTOS in your system where there is a lot of licensing fees associated with it, then in the future, if you have a startup company, okay, and you want to commercialize your product, you may end up having to pay licensing fees for every product that is shipped with the commercial RTOS. Okay, so that is a cost factor that you need to think about. Okay, and because it is open source, in this case RTX, the community support is quite big. Okay, and a lot of people are always posting about it and commenting about their experience and the things that they have learned, okay, which is good, okay, from a developer's standpoint. Okay, of course, a lot of other uh, advantages stated here, but the key ones, okay, are things like small footprint. When you say small footprint, they are generally talking about memory. Okay, why this is important? Because you are running your OS on a embedded platform, and memory is a very expensive commodity, okay, in a embedded platform. So you definitely want to use very or the least amount of memory that you can and still achieve the full RTOS functionality. Okay, so in that sense, RTX is very good. It's compatible with many ARM cores, okay, and that is a huge advantage because ARM is the number one processor design or processor manufacturer, okay, in the embedded domain. So it is definitely a very, very good thing to have, that your OS is supported and compatible with ARM cores. Okay, of course, there are a lot of other debug and software development tools available. The one we are using now is the Keel platform, but besides the Keel platform, there are also other development environments that are equally good and compatible as well. Okay, so RTX itself is a very, very good choice, okay, for us to learn and for us to implement for our embedded project. Okay, in terms of the structure, okay, the RTL library, the Keel RTL library provides everything that we need, which is the RTX kernel, together with a bunch of other libraries that can help us with our system development. In our case, we are not actually using the rest of them. We are just focusing mostly on the RTX kernel. Okay, and within the kernel itself, okay, as you can see down here, we have the scheduler, okay, followed by all the other subsystems that we are going to be using, the mutex, the semaphores, okay, the delay blocks, and so on, okay, timing related functions. So the RTX kernel itself is very, very good, okay, and gives us the RTOS capabilities that we are looking for. Okay, the source code of the RTX, okay, it is we don't really see it fully in the Keel environment, and that is because when you create the new project, okay, we are currently importing the RTX in the library option. Okay, so if you remember the steps given in the lab handout, okay, when we create the new project, the RTX, we choose the option as library. Okay, you can choose the option of source, and then you can see the full list of all the RTX or RTOS related functions. Okay, so that is an option if you are interested to look at all the RTOS related functions. But since we are using the RTX RTOS as it is, okay, it is generally easy to just include it as a library, okay, for all our lab work as well as the project. Okay, so let's come back to a bit of the aspects of RTX and OS. So we know that the first step is, of course, after we initialize the kernel, okay, we want to create a task, okay. When we create a task, okay, there are two things associated with the task that we need to know. Firstly, there is this task control block. The task control block is associated with the task, and what does it do? It gives a lot of information on what is its current priority, what is its state, what are the attributes associated with the task, and so on. The other one is the context of the task. Okay, so what is the context of a task? The context of a task includes the memory, okay, that is used, okay, for the thread stack, and a copy of all the content of the CPU registers used by the thread. Okay, so you have to remember that when the thread is running, okay, or a task is running, okay, it is basically making use of the CPU as if it is the only process or only code that is running. Okay, so it will make use of memory, it will make use of all the registers that are available in the processor. Okay, but as we have seen, okay, any point of time I may be context switched out to another task. Okay, so when that happens, I need to make sure I am able to save that information, okay, and restore it back later. Okay, restore it back later. Again, every task has its own context, that means its own copy of the variables that it was using, the registers it was using, and so on. Okay, and in order to make sure that I'm able to switch to another task and come back, okay, to where I left off, I need to be able to do this context switching very safely. And the process is very simple. If I'm currently in task A and I'm going to do a context switch over to task B, I need to save my current context and then restore or load the context of task B. Okay, so when you say context, that means it is the entire snapshot of where I left off, okay, the last time I was executing that particular task. Okay, so once I load back this snapshot, I can carry on from exactly where I left off. Okay, so that is context switching. Now, in terms of scheduling, okay, we know that the RTX employs a prioritized scheduling. Okay, that means tasks that are having a higher priority will be dispatched first, and will be able to preempt lower priority tasks. Okay, but of course, one of the things that we need to factor in is things like critical section, okay, and dependency. Okay, So can a task, okay, in its critical section be preempted? Okay, so this is something we discussed earlier when we talked about mutex. Okay, the whole idea is, if I'm going to be preempted, I want to be able to protect this information, okay, by using mutex. Okay, so that is what we have seen in the tutorial and in the lab. Okay, but because of this idea of mutex, we also know that there is this problem or this challenge of priority inversion. Okay, now let's look at this scenario. You can see that in this first example here, task 1 acquires a resource R over here. Okay, and at this point of time, there is a context switch over to task 2. Okay, and when task 2 tries to do another lock or another mutex acquire, it gets blocked. Okay, it gets blocked because task 1 acquired it but hasn't released it. So I need to switch back to task 1. Okay, in this case only 2 tasks, so once I get blocked, I switch back to task 1. Okay, and then I carry on, and only when I release, okay, then this is task 2, okay, which has a higher priority than task 1, will transition from blocked. Okay, so this is the block state. Okay, at this point you go to ready and then go to run. Okay, and once I go to run, then I can take the mutex, okay, and carry on with the critical section of the code over here. Okay, so that is basically how critical sections can be protected in a preemptive OS. Okay, but of course this idea is a challenge, okay, when we are talking about another task coming in between. Okay, so right now what we saw is the duration of the block is from here to here. Okay, it is basically the duration where the lower priority task is still executing the critical section and then releasing it. Okay, but as what we saw in the tutorial, what if there is another medium priority task, task 2? So this is low priority, this is medium, and this is high. So when a low priority task is running, okay, and it acquires the resource first, okay, and after that it gets preempted by a medium priority task, and after that a high priority task. Okay, when the high priority task is running, and let's say it tries to acquire the same mutex, but it was already locked by the low priority task, what happens? It goes to a block state. So the high priority task goes to a block state over here, and then when it goes to a block state, the low priority task, the medium priority task will then be allowed to run. Okay, and the medium priority task will run until a point of time where it is giving up the CPU. Okay, then only the lower priority task can run and complete the critical section, okay, and release the mutex. At that point of time, the high priority task is able to acquire the mutex and then go from blocked to ready to run and then finish up its critical section. Okay, so this is an issue because this time duration of task 2 is what we call unbounded. Okay, why we say unbounded? Because we do not know how many or how long task 2 is going to take before it will eventually allow task 1 to run. Okay, and it can go on for very long, especially if the situation such that task 2 is not having any form of blocking call, okay, that will put it into a block state. So it may end up having the ability to run for a very long time, and then only task 1 runs, and then eventually task 3 will run. Okay, so this is counterintuitive to our idea of priority in the first place, correct? Okay, when we say task 3 is high priority, means we want it to have very immediate access to the CPU, but in this case we are not seeing that, okay, because of this low priority task that is holding on to the shared resource. So how do we do it? How do we go about resolving this issue? And what RTX does is again something that is quite common in most RTOS platforms, which is what we call priority inheritance. Okay, in priority inheritance, what happens is the moment a high priority task, so this is high, this is medium and low, the moment a high priority task tries to lock a mutex and it is unable to lock it because a low priority task already took it. Okay, so at this point of time, what happens is the low priority task is raised to be the same priority as the high priority task. So task 1 and task 3 will have the same priority. And why is this important? Because that means when task 3 gets blocked, it will automatically allow task 1 to run. Okay, in this situation, there are only 3 tasks. So when task 3 gets blocked, it will allow task 1 to run, and task 1 will run and release the shared resource or release the mutex here. That will allow the task 3 to immediately get the mutex and carry on to finish the critical section. Okay, so it is not affected by the task 2 in this situation. Okay, so the priority inheritance is a very important aspect, okay, of the OS that helps us to prevent a priority inversion problem. In priority ceiling, the priority of the low priority thread, okay, is raised immediately, okay, whenever it acquires a shared resource, okay, and once it releases this shared resource, it is restored back to its original value. Okay, this priority that is raised to, it is basically the highest of all the threads that are accessing this same resource. Okay, so that is why we call it the priority ceiling. So the main difference between priority inheritance and priority ceiling is that in priority inheritance, uh, we wait for the event where a high priority thread is blocked, okay, because it tried to acquire a resource that was already acquired by a low priority thread. So at that point of time, the priority of the low priority thread is raised. Okay, but in priority ceiling, we do not wait for that to happen. The moment a low priority thread acquires a shared resource that is also used by a higher priority thread, we will immediately raise the priority of the low priority thread. Okay, so that is basically what is summarized here. PCP always raises the priority, okay, regardless of whether a high priority thread is blocked or not. Okay, for in our case, the RTX RTOS already implements priority inheritance protocol, so that helps us to solve the priority inversion problem. Okay, so just a quick recap on RTX scheduling options. Uh, Basically, what we know is most RTOS, okay, use this preemptive scheduling approach where each task is given a different priority, and the task with the highest priority is the one that will be chosen to run. Okay, and basically that happens through preemption. Okay, in round robin scheduling, the another way of scheduling tasks is where every task is given an equal priority and they run for some fixed period of time, what we call a time slice, and then you sort of give up the CPU, okay, and allow another task to run. Okay, so that is round robin scheduling. In cooperative, okay, scheduling, basically each task has the same priority, okay, and each task will run, okay, until it reaches a blocking OS call or voluntarily use the CPU. Okay, now the only difference between round robin and cooperative multitasking is there is no particular time slice. Okay, so in round robin there is a time slice. In cooperative multitasking there is no particular time slice, but each task will run, and when it uh, has done what it's supposed to do, it will voluntarily give up, okay, or it will give up through a blocking call. Okay, so that is the main difference between round robin and cooperative. And from what we have seen in our labs and our observations, we know that our RTX basically is by default using the round robin preemptive approach. Okay, and why is it round robin preemptive? Because every task is given a priority, and the highest priority task will always get a chance to run. Okay, the round robin nature comes in because tasks that are of equal priority get to share the CPU. Okay, so it is a mixed approach where it's round robin together with preemptive. Okay, so that is the RTX scheduling default setting that we will be using, okay, for our labs as well as our project. Okay, so that brings us to the end of this chapter. Okay, and in the next chapter we will look at a few other interesting concepts which are related to synchronization and data passing. Okay, and yes, so I'll see you in the next lecture. Thank you.